Our solar system is an exciting place. One of the most exciting developments in the past few decades has been the realization that our solar system is not unique. There are solar systems all over the place, and we're starting to learn something about them. And it seems very fitting to end this week of solar system science with some discussion of what it is that we've found out there, the topic that goes under the name extrasolar planets, or exoplanets for short. And so the fact that planets should exist around other stars and that the sun is not unique in having planets is an old idea. The fact that we saw protoplanetary disks around stars suggests that many stars will have planets. And people have been looking for planets around other stars for a long time. The first successful discovery was in 1988, so only 20-some years ago. By now, at last count, there are 853 confirmed planets orbiting 672 different stars, so we have whole solar systems that we have found. And the field is growing very fast. I think we're just starting to learn what these extrasolar systems have to teach us. Finding planets is a tough business. What you're looking for basically is a chunk of rock or gas that is not hot and is not glowing, and is very near to something, a star, that is hot and is glowing. So it is a difficult problem trying to actually see a planet at great distance. We see the light of the star, but seeing the reflected light off of a planet is a difficult proposition. Despite this, it has been applied. In all, 32 planets in 28 systems have been actually imaged. In other words, were found in actual images of the star. The way this is done is the same way we will learn next week. Technology developed to image the outer regions of the stars of the sun, the corona. One basically superposes a disk that blocks out the starlight into one's telescope and then looks for the dim lights around it. There are future missions that are designed to specifically image extrasolar planets, and we might be able to increase the rate of discovery, and one can learn a lot about a planet if one can actually image it. But most of the 900 planets we've seen have not been discovered that way. In fact, most of the time, all you can see is the light of the star. So how does the light of a star tell you that there is a planet orbiting it? The following few simulations might help understand that. One key to understanding how a star can tell us that a planet is orbiting it is to remember that if a planet is orbiting the star, then the star is also orbiting the planet. In fact, they are both orbiting their common center of gravity, as this animation here will show us. We have here a planet and a star. I have, just for the purposes of discussion, given them a mass ratio of 1:4, and what we see is that they each orbit, I've assumed a circular orbit, and they each orbit in a circle about the relative common center of mass, which is here this green X. And what we see is that the radii of the two circles are, of course, distances from the center of mass. In other words, if the larger star here is 4 times as massive as the smaller planet, then the radius of the orbit in which the star orbits is 1/4 the radius of the orbit in which the planet orbits. In other words, if this orbital radius is our star and this orbital radius is our planet, then since they're orbiting their center of mass, these satisfy mass of the planet times the radius of the planet's orbit is equal to the mass of the star times the radius of the star's orbit. And of course, the distance between the planet and the star, since they're on opposite sides, the distance is simply rs plus rp, the sum of the two radii, and this distance is constant at all times. Of course, most planets don't orbit in circular orbits, but as usual, we will make that simplifying assumption. It'll help us make calculations more straightforward. Of course, since typically a star is far more massive than the planets that orbit it, the star will move in a far smaller circle than will the planets, and detecting the motion of a star might be difficult because the motion is very small. To give us a sense of how this works, we'll try to imagine detecting from a distance the planets of a solar system we understand, namely our solar system. And indeed, because Earth orbits the sun is also orbiting the Earth. the center of mass of Earth and Sun lies well deep within the Sun, and it would be very difficult to actually note the motion of the Sun. In fact, the only planet whose common center of mass with the Sun lies outside, just outside the surface of the Sun, is Jupiter. And in this animation, we see that if we take into account only the gravitational effects of Jupiter, then we observe the Sun moving around in a circle around a point just outside the surface of the Sun. Saturn's influence is the next most remarkable, and because we now have two periodic motions, the Sun's motion is a little bit more complicated. It no longer moves in a circle, so by doing some interesting analysis, we could in fact disentangle perhaps the two motions due to the Sun and to Saturn and Jupiter, if we could observe this motion. So we need to understand how far the Sun is moving and try to see what limits this places on our ability to detect planets. So now we have an idea. Maybe we can observe that a planet is orbiting a star by watching the star wobble. We need to understand how much the star will wobble. We expect it not to be very much, but because it is a periodic motion, we might be able to actually distinguish it and realize that what is going on is that there's a planet orbiting it. And we said that if we assume circular orbits, if there's a distance r between the star and the planet, then we can write r as r is the radius of the circle in which the star moves, plus the radius of the circle in which the planet moves, and the two radii are determined by this center of mass relation. And plugging one relation into the other, I see that the total distance is rs plus rp, but rp is rs times ms over mp. We write it this way, and now I can solve this equation for rs. Rs is equal to r divided by 1 plus ms over mp, and then I can pick a common denominator on the bottom to write mp plus ms, and mp comes here. mp plus ms is nothing but the total mass, which I'll call n. And this is not surprising. The amount by which the star moves is related to the distance between the two by the ratio between the planet's mass and the total mass. The larger the planet, the more the star will move. Not too surprising. Let's see what that tells us. For example, about an idea. Let's try to detect Jupiter. How far would the Sun move? Well, plugging in this result we just figured out, I find that the radius of the circle in which the Sun moves due to the gravitational effect of Jupiter is the ratio of the mass of Jupiter to the mass of the Sun times the radius of Jupiter's orbit, which I've put in here, and that's indeed right outside the Sun. This is 740,000 kilometers. The Sun itself is about 696,000 kilometers in radius. This point lies right outside the Sun. Detecting the wobble of a star due to the effects of a planet that orbits it is going to be difficult. In fact, of all of the planets that we know, one was detected by this method. This is called astrometry. So, finding the motion, discerning the motion of the star is not going to be our most successful strategy. What else can we do? Let's go back to the simulation and see a different approach. The secret, it turns out, is that while it is very difficult to measure the position of the star with the precision necessary to detect a planet surrounding it, we may be able to detect its wobble by measuring its velocity. How can you measure velocity without measuring position? That's an interesting question. Well, there is a sense in which we can measure velocity directly without measuring position, and this is the Doppler effect. Remember that the spectrum of a star will contain absorption lines for whatever gases are in the star's atmosphere, as we saw for the spectrum of the Sun. If you can identify a particular absorption line and find that it is shifted in frequency or in wavelength from its natural wavelength, we can use the Doppler formula. I remind you that lambda is lambda 0 times 1 minus v over c, where c is the speed of light and v is the speed with which something is moving. Since spectral lines are very, very narrowly known, we can measure rather small velocities compared to the speed of light, in fact down to a few meters per second, so 1 part in 10 to the 8th. We can make pretty accurate velocity measurements provided there is a Doppler effect. Remember, the Doppler effect only obtains if the object, the source of light, is moving towards us or away from us. So in the position that this animation currently depicts, of course, we have no such luck because as the planet orbits the star and the star orbits the planet, there is no motion at all, no change in the star's distance from us, so there is absolutely no radial velocity component. The star or the planet neither approach us nor recede. On the other hand, if I tilt and I imagine that the system happens to be oriented in this direction, then what I observe is that now the planet, and therefore the star, periodically approaches Earth and recedes from Earth, and maybe we can detect the variations in wavelength of some absorption line by measuring the velocity with which the star is moving. And the way we do this is precisely by doing spectroscopy. Let's take a look. This animation sort of shows you the setup. We have here a planet orbiting a star, therefore the star orbiting the planet, albeit in a much smaller circle. We cannot see the planet, but we can see the star, and things here are perfectly aligned. The motion of the system is in such a plane that the entire velocity of this vector of the star will be visible to us. There is no motion out of the plane of this image, which would be invisible to us. And we observe some absorption lines in the spectrum of the star, and when the star is receding from us, the absorption lines are shifted to the red. When the star is approaching us, they're shifted to the blue, and we see this periodic shift in the Doppler shift in the absorption lines, and by detecting the periodicity, we can measure the period with which the planet orbits the star, and perhaps learn some more. Of course, the Doppler shift here is greatly accelerated. Let's do a little calculation to see what kind of velocities we'd be trying to detect. So perhaps the way we can detect the fact that a planet is orbiting a star, hence the star orbiting a planet, is to hope that the orientation of the orbit is such that at least some fraction of the star's motion is radial towards us or away from us, and we can use Doppler shifts to detect that velocity. Let's figure out how fast the star would be moving. So we have this system. How fast is the star moving? Well, the star moves around a circle of radius rs, as we said, and it moves with a velocity, a speed, vs, whose velocity is continually changing. So as we know, the acceleration from our second week of class, the acceleration with which the star accelerates towards the center is vs squared divided by rs. And if I multiply this by the mass of the star, this is the force acting on the planet, on the star, to accelerate it. And of course, this is Newton's gravitational force. In other words, this is g times the mass of the planet times the mass of the star divided by the square of the distance between them. So let's put that in. Here's our equation. What do we do with this equation? Well, of course, we first realize that the mass of the star completely cancels from here. This is characteristic of gravity. Now, what I want to do is figure out v. I want to know how fast the star moves. So from here I have that vs squared is given by g times the mass of the planet times the radius of the circle in which the star moves divided by r squared. But it would help to remember that we computed that the radius of the circle in which the star moves is related to r by the mass of the planet divided by the total mass. And so using that in here, I find that this is g times the mass of the planet divided by r squared times r times the mass of the planet divided by the total mass. And what I find is that this is given by well, I can cancel one of the r's here, and I find that vs squared is g times the mass of the planet squared divided by m times r, which is almost nice, except I will find it more convenient to write g times m divided by r. This is a quantity with the dimensions of velocity squares, times ratio of the mass of the planet to the total mass squared. All I've done here is multiply and divide by the mass, the total mass. And so this is my expression for Vs. And when I plug it in, I see that the following things are true. For M is usually typically just the mass of the star. The mass of the planet is small anyway. What we see is that massive planets will cause more motion. This is certainly true. But unlike the case when we were trying to do astrometry, in the case of radial velocity measurements, the closer a planet is to its star, the smaller r, the more radial velocity the star will acquire. So this method will be useful in discovering planets that are massive and orbit close in. We can solve this equation now for Vs by taking the square root, and this is the expression we get. Again, the largest values of velocity will arise from heavy planets that orbit near their stars. We can plug in the numbers for Jupiter. If you look at this quantity in the square root, it's simply the orbital velocity of Jupiter to good approximation. And so plugging in the numbers, we see that due to Jupiter orbiting it, the Sun moves at 12.5 meters per second. This is a small velocity relative to the speed of light, but wavelengths can be measured with extreme precision. We would have very little trouble if orbits were aligned correctly, identifying the motion of the Sun by 10 meters per second. And in fact, this is one of the most productive ways of detecting extrasolar planets. A total of almost 500 planets in almost 400 solar systems have been detected by what we call radial velocity measurements. And remember, this is only possible for systems so aligned that part at least of the motion is radial. If the system happens to lie so that the motion of the planet and the star is perpendicular to our line of sight, there just is no radial component, there is no Doppler shift. We're out of luck trying to find it. Despite this has been one of the most productive ways of measuring it. But if the system is aligned properly, we can do even better. Let's check this out. One great advantage of the radial velocity measurement detection is that if we have some way of estimating the mass of the star independently, we'll see that we have such methods, then it gives us information about the mass of the orbiting planet as well as the distance at which it orbits, and so we can extract the beginnings of more data about what kind of planet we see in what kind of orbit. Under some circumstances, if the alignment is just right, we can do even better. If the alignment is such that the planet in fact transits in front of the star, then the planet will partially eclipse its star. And the way we will observe this is that the starlight appears to dim when the planet is transiting. And we call this measurement measuring the light curve. The light curve is the dependence of the brightness of the star on time. And what we will see is a periodic change as the brightness of the star dips periodically when the planet transits it. We can use this to compute the period. We can use this to study from the details of the shape of the light curve. We can learn many things about the planet, and such as its size, its mass. If we're lucky, we might even see the planet's atmosphere beginning the eclipse process and see the star through the planet's atmosphere and attempt to do spectroscopy and understand the chemistry of the star's atmosphere. So in principle, the transit method is a very constructive method which gives us a lot of information. Some 300 planets in over 200 systems have been detected. There's a dedicated space telescope, the Kepler Space Telescope, which is doing a survey of the sky and already has over 2,000 candidate planets in over 1,000 candidate systems, but the transit system, the transit method is not considered a complete detection until verified by some other means, so these are undergoing verification. The sample of planetary systems that we have outside the solar system is certainly growing very quickly, and we should have a lot of information. Ideally, one detects the same planet both using radial velocity and transit method, and then one can extract lots and lots of information. We will talk more about transits when we talk about binary stars and light curves. There are a few other methods that have been used. The light of a star can be intensified by the presence of a planet, and some 16 planets have been observed this way. If we have one transit planet, we can study its orbit and find perturbations to its orbit and ascribe them to another planet and learn about the existence of the other planet in the same system. Some planets have been detected this way. In all, we're compiling a collection of solar systems, and it behooves us to see, well, how do they stand to our understanding? How did this match our understanding of our solar system? We developed sort of a good theory that describes the one solar system in the universe, but now that you suddenly have thousands of them, you can ask, does this theory work? And so, what have we found? As this image clearly shows, we haven't looked very far. We've looked to about 300 light years around the solar system. That's a tiny fraction of the galaxy. We have all these thousands of planets. Depending on how exactly you make the estimate, and as I said, this is a young science, between 1 and 40% of sun-like stars have planets. Either number means that in a galaxy with a few hundred billion stars, there are lots and lots and lots of planets and planetary systems all over the place. No, the solar system is not unique. Now, the methods that we've used, both the most constructive ones, both the transit method and the radial velocity measurement method, are most sensitive to what we call hot Jupiters, planets that are very massive and orbit very near their star. Remember, we saw that with the radial velocity measurement. It's also true that it's more easy to arrange an alignment if the planet is close. Our methods are sensitive to hot Jupiters. Maybe it's not surprising that mostly we find, at least initially, lots of planets with masses similar to or larger than Jupiter's orbiting in Mercury-sized orbits. Now, well, yes, there is a sample bias going on here, clearly a selection bias. If one had a detector that was only sensitive to unicorns and one found no coyotes, this would not be a surprise. But if one had a detector sensitive only to unicorns and found unicorns, that would still be a discovery. Discovering all these gas giant planets orbiting within a half an astronomical unit of a sun-like star should still be jarring because, remember, we explained at great length why it is impossible for such planets to form so close to the star because the solar nebula is too warm and volatile materials are not solid. What we learn from the fact that they exist is presumably they did not form in that position. They formed farther out where the nebula was colder and migrated in. So the kind of migration that the NEAS model proposes for the solar system apparently is occurring all over the place. And this indeed seems to be a ubiquitous feature of the solar systems we're finding. The kind of sedate stability that we see in our solar system is not actually the standard. There's lots of strongly interacting, very resonant orbits, instabilities. In that sense, at least, the orbits we find in our solar system are a little bit uncommon. What are the planets like? Well, again, most of the planets we find are very massive, and lots of them are very close in. If you look at this logarithmic plot, right in the center of the plot, over down here, is our Earth, and then the horizontal axis is the distance from the star. The vertical axis is the mass of the planet. Both of these are logarithmic. So most of the planets that have been found are much more massive than Earth. In fact, much more massive than Jupiter up here. And many of them orbit very close in. These are these hot Jupiters that we spoke of. But we're also finding planets that orbit out at far larger distance from their stars. And we've even found some planets that are on the order of magnitude of Earth's mass or less. And so if you take the selection bias into account, the prediction is that, in fact, this data suggests that there are Earth-like planets in much larger numbers than there are Jupiters or gas giants, because the fact that we're detecting them at all means they're far more common. We also find some super-duper Jupiters, some gas giants with masses 15, 20 times the mass of Jupiter, much larger than one thought planetary systems could create, and some interesting, strange cases like a planet called Kepler-16b that orbits a binary system. So two stars orbiting each other with a planet in an almost perfectly circular orbit around the center of mass of the system. This had been thought to be impossible to arrange in a stable orbit, and Kepler-16 shows us that nature manages to find a way. So the field of extrasolar planets is, despite the fact that it's been a few decades since we first discovered the first ones, this is really a field in its infancy. We're just starting to learn what we can learn from these exciting systems. And I anticipate a lot of news, both in terms of discovery and in terms of insight into how solar systems work in the coming decades. Let's sum up a busy week. Well, we found a lot to learn right in our own solar neighborhood. A lot of it, both in our solar system and certainly beyond, is just being learned. I hope you are starting to develop an appreciation for the fact that we tried to understand some of the fundamental physics, because wherever we can apply it, we can actually understand what is going on. We can make calculations that tell us what to expect and match them to experiment. I think understanding the physics, roughly, of the greenhouse effect might be a good example of this. And as I said, exoplanets are probably going to eventually completely change the way we think of solar systems, and so stay tuned. We've not covered many of the interesting topics in the understanding of our solar system. I want you to think of this week more as a hunting license. You now have the tools to go and read about the moons of Jupiter and why it is bizarre that Neptune has a moon that orbits completely outside the ecliptic, what that probably tells you about Triton, and so on and so forth. And so I think you are equipped with at least the tools to go and acquire information. Next week, we aim for the stars.